Let's talk about recursion. The standing joke among computer scientists is that the definition for recursion in the dictionary says, see recursion. The definition you see here actually alludes to that fact with the first listing. The third listing is a more complete and understandable definition. The phrase calls itself is the key to a recursive method and is what you would look for in determining whether or not a method is recursive. Stop the video for a moment and read through this definition to get a better idea of this concept. Recursion is another way to repeat processes in a program, different than how a loop works. Generally speaking, anything done by a loop can also be done by recursion, but the converse of that is not always true. In some cases, recursion is the only way to do a repetitive process that cannot be done by a loop. The recursive process involves defining a method that calls itself, stacking up method calls in memory, partially completed, waiting on information from the next recursive call before completing the call to the current method. The basic control structure inside a recursive method is an if-else statement, where one part of the if result is a recursive case and the other is the base case. The base case is critical to any recursive call. It is the one that stops the recursive stacking process. If you don't have a base case, it causes infinite recursion, which is very bad since it uses up all the working memory of the computer and locks it up, and you just have to restart. The action for any part of the recursive method can be anything: an output, a calculation that is returned, a recursive call, or any number of things. Recursion is kind of like a version of the old telephone game you used to play at parties, except now each person asks his neighbor for an answer and then does something with that answer. Let's listen in on this interesting conversation. Howdy, neighbor. Someone called me asking for my number, but I need yours first. Then I'll add 1 to it to get my number. Sure, honey. Can you hang on a minute? I have to get my other neighbor's number, and I will add 1 to it to get mine. Then I'll give it to you. Hey, neighbor, what's your number? I need to add 1 to it to get mine. My neighbor's asking for it. What? Okay, I'm trying to sleep here. I'll get my other neighbor's number, and then add 1 to it to get my number. Then you can have it. I'll go back to sleep. Hey, girl, what's your number? I need to add 1 to it to get mine. My neighbor wants it. Oh, okay. Hang on a sec. I have to get my other neighbor's number. Then I'll add 1 to it to get mine. Then I'll give it to you. Hey, buddy, what's your number? I need to add 1 to it to get my number. My grumpy old neighbor is asking for mine. Sure, no problem. I am the base case, so my number is 1. Awesome, thanks so much. I'll add 1 to your number, which makes mine 2. Hey, neighbor, I have my number. It's 2. Thanks. I'll add 1 to it, which makes my number 3. Okay, I have my number. It's 3. Hope you're happy. Now leave me alone so I can get back to sleep. Thanks. No need to be snippy. I'll add 1 to it, which makes my number 4. Neighbor, I have my number. It's 4. Thanks so much. I'll add 1 to it, which makes my number 5. I can now give it to the one who called me. Have a nice day. Well, that was interesting. Let's examine this recursive method. First off, the value of the formal parameter x is printed. Then the if statement is checked for true. If it is true, the recursive call is made with 1 less than the value of x. This is like the step in a loop, moving towards the stopping condition for recursion, which is the base case. The base case for this method is implied. Nothing happens when the if is false. Control just proceeds to the last print statement. Let's look through this process step by step. So here we have a call to the doStuff3. The job of doStuff3 is to print itself and then call doStuff2. doStuff2 prints itself and then calls doStuff1. doStuff1 prints itself and then calls doStuff0. Since do stuff 0, the value 0 makes the if statement false, all we do is simply print 0 and then print done with 0. Do stuff 0's job is done, so control goes back to do stuff 1, which prints done with 1. Its job is done. Do stuff 2 says print done with 2. Do stuff 3 prints done with 3, and the whole process is finished. Now let's look at this next example. Stop the video for a second, notice one very slight change, and see if you can predict the output. All right, let's see how you did. The call to do stuff 3 immediately calls do stuff 2, which immediately calls do stuff 1, which immediately calls do stuff 0. Now, when we get to do stuff 0, the if condition is false, the action for the if just doesn't happen, and we simply print 0. Do stuff 0's job is done, control goes back up to do stuff 1, which can finish, then do stuff 2 can finish, then do stuff 3 can finish, and now the whole process is finished. Now here is an advanced process that includes a binary tree. And you may not have studied binary trees yet, but this should be a simple enough example to follow through. When you do study binary trees, you may want to come back and take a look at this again. So here we have a tree that is consisting of several nodes. Each node has a character as a piece of data, and then it has a left and a right subtree, which points to another node. Notice the ones at the bottom, those are leaves. They have no children, so they're not pointing to anything. They just have data. So when we traverse this tree, we start at the top of the tree and traverse H. Well, the first job for H is to print itself, and then to visit its left and right subtrees. So we visit the left subtree of H, which is G. Well, H can't finish traversing its right side until G has finished, so G prints itself. It traverses its left side. Same thing, G can't finish until F has finished. So we go down to F. Since F has no children, the only thing it does is print itself. Method F is finished, and now we can traverse the right side of G, which is H. Since H is a leaf node, it just prints itself. Its job is done. G's job is now done. And now H can traverse its right subtree, which is K. K prints itself. It traverses its left tree, which is I. It prints itself. K can now traverse its right side, which is M. It prints itself. M is done, K is done, and H is done. This is what's called a pre-order traversal, a classic traversal of binary trees. Now look at the next example and see if you can spot a difference and predict the output. Stop the video, study it for a minute, see what you come up with. All right, let's see how you did. We traverse the tree starting with H, but notice the print statement is now in between the left and right subtree traversal calls. So H left is traversed, which is G. G then traverses G left, which is F. F just prints itself, goes back to G, which prints itself, and then traverses right. Traverses H, which just simply prints itself. It's done. G is done. H prints itself and then goes right, which is K. K goes left, which is I. I prints itself. We can print K now. We go to the right side of K and print it. M is printed. M is done. K is done. H is done. The whole process is over. This is what's called Inorder Traversal, another of the classic traversals for binary trees, and one again that you cannot do with loops. This process can only be done with recursion. Generally speaking, recursion is a process of a method calling itself over and over again until a base case is reached. It uses an if-else statement as its main control structure.